Hello, this video goes over the design methodology needed for your multi-stage transistor amplifier. In this video, we're going to go over some applied steps to take to design the multi-stage amplifier. There'll be some equations in this video, but I am not going to go into explaining them, and if you need an explanation, definitely look in your workbook activities and the workbook activity videos in Canvas. So first off, I wanted to go over the lab objectives. So design a 3-stage discrete transistor amplifier using small signal BJT transistors. Your amplifier must be able to amplify a 1 kHz sinusoid of amplitude 10 millivolts without distortion and be able to drive a 10k ohm load. So an amplitude of 10 millivolts is 10 millivolts peak. And 10 millivolts peak is also 20 millivolts peak to peak. So when you're in the lab using the lab equipment, or if you have a signal generator at home, it's important to know the difference between amplitude or 10 millivolts peak and 20 millivolts peak to peak. So the amplifier specifications, the power supply should be 20 volts. The maximum current supplied to the amplifier should be less than or equal to 10 milliamps. The midband voltage gain should be approximately 100. The input resistance, so the input resistance will be the input resistance of the first stage, should be greater than or equal to 100k ohm. That is extremely important. The output resistance, which is the output resistance of the third stage, should be less than or equal to 500 ohms. The lower cutoff frequency should be less than or equal to 100 hertz. The output voltage swing, the max peak to peak, should be equal to or greater than plus or minus 5 volts, and the minimum load should be less than or equal to 10 kiloohms. So in the circuit, you're using BJT transistors. This is like your 2N3904 or your 2N2222. Another common one is your 2N5088. There's a lot of different BJT transistors that you can use, and it's important to look up the data sheet and at least just see what the pinout is, because some of these BJT transistors do have different pinouts. So all the resistors need to be between 100 ohm and 10 megohms, and all the capacitors need to be between 100 picofarads and 10 microfarads. So just to go over an overview of the different amplifiers, your common emitter amplifier has high gain, and the input and output impedance are moderate. So the common emitter amplifier is really good at creating gain. The common base amplifier also has high gain, but it has a low input impedance and a high output impedance. So the common base could be very difficult to incorporate into your amplifier because of the low and the high input and output impedance. But the common collector amplifier is really good at matching stages. So the gain is unity theoretically, and applied it's less than 1. The input impedance is high and the output impedance is low. So because it has a high input impedance, if it was connected to anything with a low input impedance, it would be able to match the signal better, and it wouldn't attenuate the signal that much. And because the output impedance is low, it's really good at matching low input impedances or even high input impedances. So this is an example of the multi-stage amplifier. This is the one that I made when I took the class. So over here in the blue box, we have the signal generator, we have a series resistor, and then in the orange box, we have a common emitter amplifier. And I want you to notice, right, because a common emitter amplifier is good for gain, but moderate input impedance and moderate output impedance. So one of the objectives is to have 100 kilo ohm input impedance or higher. And because the common emitter is not that great at that, I had to use a really high R1 at 10 megs, and the R2 is 620 ohms, 10 meg ohm, 620 ohms. And then on top of that, I had to add this series resistor to be able to accomplish over 100 kilo ohm input impedance. A solution to that would be using a common collector in the very first stage, because common collectors have really high input impedances and really low output impedances. So another thing I want you to notice is the common emitter amplifiers that I'm using are called swamped, and this is your swamping resistor. So the swamping resistor will decrease the gain of a common emitter amplifier, because the gain of a common emitter amplifier is predominantly RE1 and the diode resistance, right? So RE1 is your swamping resistor, R prime E is your resistance of the diode, and this isn't going to affect your gain, and that's because the signal comes in, and what does it do? It gets shorted, the AC signal gets shorted through the capacitor. So that's why I use the swamping resistor, and I use the swamping resistor on this side. Also, in the objectives, it talked about the minimum and maximum components. Ideally, I would use a 20 microfarad capacitor here, or a 22 microfarad capacitor is a really common value, but I just put two in parallel, right? Because I had to use 10 microfarad and another 10 microfarad, so I just put them in parallel to accomplish the amount of capacitance that I needed. So these two amplifiers are used to increase the gain, and then the common collector was used to match the signal, but primarily to have a low output impedance. So, the first thing you're going to want to do, let me go back, the first thing you're going to want to do is just make one amplifier and then run the numbers, right? Do your DC analysis and your AC analysis, figure out what your R in and your R out is. And then after you do that, try another amplifier. Like, if you want to do two common emitter amplifiers, if you want to do a common collector amplifier, and then, one of the biggest things you're going to see is the output impedance or output resistance of this amplifier is going to affect the input impedance of this amplifier. So that's one of the more challenging things about creating the multi-stages, is knowing that the impedances, like the output impedance of this stage, you would treat it almost like a series resistor and just call it, I called it ZN for my lab that I did. And then once you have two of them, then try it again. It really just takes practice. Like at this point, you're probably pretty good at doing one, but it just takes a little bit of practice and really just plugging and chugging the numbers and iterating and going back and figuring out what you need to tweak a little bit to get these things to work the way you want them to. So this is a block diagram. I did my block diagram after I crunched the numbers a million times and got the circuit to work the way I wanted it to. And one thing I want you to notice is the stage 1, right? The loading factor, which is pretty much a voltage divider without the voltage, it's just Rn over Rn plus Rout. The loading factor is 0.56, so it cuts the signal down by almost half. And then the second loading factor cuts the signal down by 0.63, which is a little better. So in an ideal world where there's no loading factor, you would want your common emitter stage 1 to have a gain of 10 and another common emitter stage to have 10, right? Because 10 times 10 would be your gain of 100. But because of the loading factors, you're going to want these to have a much higher gain because they're going to get attenuated. So once you make your schematic and you've experimented and like crunched the numbers, definitely use this block diagram and like do the formulas for these and figure out the gain and the loading factor for each stage, and then like plug the numbers and see what your gain is, like your overall gain. Another issue is the loading factor of the signal generator, right? So if you're sending a 20 millivolt peak to peak signal out of the signal generator, the signal generator's impedance is 50 ohms. So you would plug that into the input impedance, or the Rn of your first stage, and the output would end up being a little less. It would be a little attenuated because of the input impedance of the signal generator. So, for mine, I had a 20 millivolt peak to peak coming out of the generator, but by the time it actually went into the amplifier, it was 18.59 volts peak to peak. So I suggest just starting with one amplifier, doing the DC analysis, do your AC analysis, and then like grow it from there. And one thing I wanted to go over is the max peak to peak values, because you're going to build your amplifier, you're going to get your input impedance really good, you're going to get your output impedance at a really good level, and then you're going to realize, oh yeah, what's this max peak to peak that I need to have over 5, plus or minus 5 volts. So your max peak to peak is actually 2 formulas, and I'm going to pull up an Excel spreadsheet. So your max peak to peak is 2 formulas that you compare, and the smallest value is your max peak to peak. So you can see for here, this formula gave me 6.48, this formula gave me 7, so I took 6.48. If you have experience using Excel, it will really come in handy to just start making yourself an Excel spreadsheet for this lab early on, because you're going to use the iteration process, and you're going to go back and you're going to recalculate this amplifier. You're going to make little changes, see how it affects the circuit, see if you can get the input and output impedance you want, the max peak to peak, and by just changing a couple numbers here and being able to have all of these values change is going to help save time rather than having to do it all by hand. But if you don't have experience using Excel, that's okay. Like, just do it by hand on a piece of paper and save those results, and then think about what you want to change, right? Like, so your R1 and R2 values, if you want a larger input impedance, you need those to be much larger, like I had showed you on my first stage. So with the max peak to peak values, I also wanted to show a pretty interesting formula for optimizing your emitter resistance. So using this formula, you can figure out what your emitter resistor would be for a maximum peak to peak. So your maximum peak to peak is maximized when the two formulas equal. So you can see for this result, 6.48 and 7, they're pretty close, right? So the quiescent point is pretty close to being in the middle of the load line. This is that formula to optimize the Q point, and it says 690 is what the max optimized Q point would be. So I look at RE1, which is my swamped resistor, and RE2, which is my emitter resistor, and just to go back on the schematic, I'll show you where those are. So RE1 is this one, and RE2 is this one, and we're optimizing the Q point by combining those two. What's the emitter resistance? What's the emitter resistance that optimizes the Q point? So 690, 270 and 430 is 700. So if we just decrease this one by 10, see how those are almost identical? So that's like the maximum peak to peak you will get, is when they're equal. So moving on. So yeah, start with one stage, grow it to 2 stages, and then finally try doing a 3rd stage. And you're going to do your DC analysis, your AC analysis, and your RIN and your ROut values, or your Z in, Z out, however you look at it, impedance or resistance. And you want to remember that the common emitter and common collector and common base amplifiers, they all use different formulas. So don't get confused by using different formulas. Like, just looking at Z out for the common emitter, right? Just look at that formula, and then looking at Z out for the common collector, the common collector is connected to the emitter, so it's going to have to do with RE and RL, like your load resistor, your emitter resistor, as well as Z in at the base. So it's going to have a little bit to do with your base impedance. So don't get the formulas confused, and just, if you keep going back and going through and doing the calculations, it'll help. And so just one last point that I wanted to make was, I had talked about you want your emitter, common emitter amplifiers to have more than 10, a gain of 10, right? So in my example, I had 2 common emitter amplifiers. I think one had a gain of 15 and one had a gain of, yeah, this one was a gain of about almost 16 and this one was a gain of 22. And then at the end of the day, I had a gain that was really close to like 110. But if you were to just look at those values, you would say, no, you should have a gain much higher, but it's because of the loading factor. So it's easier to make an amplifier that has more output that you need, because you can just add a series resistor in the front and attenuate the signal, right? Because if you have a series resistor, you're just adding another variable for your voltage divider. So I hope this helps, and I'll see you on the next video. Thank you.